Today I'm going to give a little training session on Foam Python, which is code that I've done sometime last year, basically, that mimics some basic functionalities of OpenFOAM, but everything is basically implemented in Python. So in the session, I'm going to give you a little introduction and a general overview of the code of the implementation. I'm going to go a little bit deeper into the code structure. And then I'm going to give some usage examples, so basically running some cases, and then I'm going to give a little simple example of writing some custom code within the software. So regarding motivation, less is more. In this case would mean that could mean two things. So basically, a lot of people find it easier to use Python for coding than C++. I'm sure that many would agree with me on one hand, and on the other hand, the thing is that OpenFOAM, as it is, has almost every fork, I think, has more than 1 million lines of code, which means that maybe some fundamental changes to the way that we do final folding method or CFD in general could be easier implemented in something that has 2,000 lines of code versus in something that has 1 million lines of code. And another thing, again, especially because Python is easier for, it is more beginner friendly for beginners in software development and etc. It might be more accessible to people basically playing around with the code and figuring out what's going on in unstructured final folding method and so on. So just a little comment on Python versus C++. So this is a screenshot from our website that says that of software developers, 27% of them said, of the ones prompted, 27% of them said that they use Python primarily as their work language, and 7% of them said that they use C or C++. So obviously there is a difference in popularity there. And basically the same as I said already. So from extent of pure C++ code, it has more than 1 million lines. And in my case, in the case of my code, it has about 2,000 or 3,000 lines of Python code. So excluding comments and everything else, scripts and so on. So yeah, as I said, basically, if you want to do something fundamentally different, which is restructure the FE mesh class, or maybe you restructure some linear algebra solvers and so on, it could be a bit easier to do in Foam Python because there is simply less dependence on higher level code when you're talking about the lower level code, such as mesh storage and etc. Disadvantage, as Python almost always is, it's slower, but I'm going to have a little discussion in general and specifically applied to my code, how that differs Python versus C++ in terms of computational speed. So some of the included physics in my code currently, so I have an equivalent of the Laplacian foam solver, which solves the transient diffusion equation as seen, and the famous flange tutorial. And regarding fluid flow, I have implemented equivalents of simple foam and icofoam, where simple and piezo algorithms are used for pressure velocity coupling, and then again some very famous examples like driven cavity flow and Pitt's daily could be solved with that. So regarding the code structure, the code is heavily object oriented, same as OpenFOAM basically. It has a lot of the same naming for classes and so on. One nice thing that is allowed because of object orientation. So it's very similar in OpenFOAM actually, but here's an example with Foam Python. So basically, you can write this equation in a sort of abstract but still tangible way, and you can basically use this kind of representing equations within the code because of the high level of object orientation. And this is exactly what I was talking about. So the top example is Foam Python, and basically how it looks in Foam Python, and the bottom is how it looks in FOAMXN 4.1. So this is the Laplacian foam solver. So basically you see dt of t minus Laplacian of t, and it's very, very similar in Foam Python, and I'll get to comment on that a bit more in the code later. So of the basic OpenFOAM classes which are present, which were basically a necessity to have all of the functionalities that I mentioned, they are FE mesh, fields class hierarchy, so volume, vector, field, scalar, and so on. FV matrix, including the FVC and FVM namespaces as seen in OpenFOAM. And the boundary conditions are handled within the other classes which construct the FV matrices, and the time is handled, and not only time, but in general, a lot of stuff is handled using existing Python functionalities. So that's also one nice advantage of Python is a lot of people use it. There's a lot of packages. It's very simple to basically Google something that you want to do and then import some existing functionality that someone already developed and wrapped in a nice little package that you can very simply import into your code. Runtime selection, as opposed to C++ and OpenFOAM, is made possible in a simple manner because Python is an interpreted language, so there is no need for complex wrappers to communicate with file storage and so on. So the code simply reads in a string as an input and points to the appropriate model using string evaluation, which is not as simple in C++. Regarding matrix storage, so the same as in OpenFOAM, it is the compressed arrow format with the lower triangle coefficients of the A matrix, diagonal, upper, so source contributions, and so on. So the same format is preserved in FOAM Python. And so far, I have implemented Gauss-Seidel and Jacobi solvers, arguably the simplest linear algebra solvers. Code inputs are handled similarly as with OpenFOAM for comfortable use. However, again, as Python is an interpreted language as opposed to compiled, which is C++, input-output functionality is simpler. Again, no need for complex communication with files, file storage, and so on. So this is an example of a case set of files, so an equivalent of a 0 folder in the case of OpenFOAM. For reading in meshes, constant polymesh is read, same as in OpenFOAM. The format is the same, so basically it's possible to read in existing OpenFOAM meshes and simply use them within code to solve whatever kinds of equations that you want to solve. Outputs, again, very simple. File writing functionality as always seen in Python, and I have implemented in a way that it's readable with PyView. To talk a little bit about some implementation details, I'm going to give actual screenshots and snippets of code and just go into that a little bit. So this is an example of the Laplacian form solver. So by the way, so in the end, I'm going to give a link for the Git repository. It's going to be possible to download it either now or after the session or however you want to do. But I'm going to go through some of the code first. So basically in this file, we see importing of general Python stuff. We see importing of FOAM Python specific code that handles the FV mesh, FV matrices, fields, and so on. So basically after that step in the solver code, we read the case set of file, which contains the boundary conditions and various other things necessary to solve our problem. And then mesh is constructed. In this case, it's constructed using this sort of a constructor. I'll come to that a bit later when I'll go into the FV mesh class. And now the code has the mesh, and that is then passed to the field T, or temperature, that is initialized. And similar to OpenFOAM, there's a string that represents the name of the field, and we're passing it some boundary conditions, initial conditions, and so on. And then the time for the simulation is initialized. And this is basically the solution loop. Quite simple. So basically, while you need to solve, if you want to reread some of the case set of files, such as boundary conditions, initial conditions, solver specifications, tolerances, and so on, incrementing time, and then basically similar to what was seen before in some of the previous slides, we assemble a DDT matrix and a Laplacian matrix of the field T. So this is mimicking the Laplacian foam equation, and then it is solved. So this is, for example, this matrix is of type FV matrix, and it's the solve function is called to solve it, and basically this is iterated and looped until a certain time or whatever is specified. And this part just handles writing of the results. This is just a little last amount of code to handle printing out total execution time, simulation end, and so on. So this was an example of a reasonably simple solver. And now to go a little bit into the FVMesh implementation. So the FVMesh is a class, and these little subclasses are something like drawers for data, like so geometry data, which would be volumes of cells, face area vectors, magnitudes of face area vectors, and so on. So basically geometrical data. And the other basically drawer for data is connectivity data. So this is basically the stuff that is seen in the constant polymesh folder, same as in OpenFOAM. So basically points, faces, owners, neighbors, and the boundary dictionary. Okay, so basically this is one difference in between Python and C++. So by definition, Python is weakly typed, which means that we cannot overload functions because you cannot pass you cannot define functions in the same way, and then depending on the type of the arguments that we are passing, it cannot decide on that because the type of the argument that is being passed can be anything. So you cannot overload constructors in Python as opposed to C++. And basically the way I went around that is I have one main constructor, which is the init function, where I distribute all of the data basically to all of the necessary, so for example, volumes, surfaces, points, faces, owners, and so on. But basically how I actually do that, I have different functions, different constructors. So this is the way I mimic the constructor overloading functionality of C++ and OpenFOAM. So this is a constructor that basically gets the polymesh location, which is constant polymesh in the case of the top level code, and then calculates all the necessary data it needs. So basically these functions just go through the folder, just read in, and they basically crunch the files. And then after that, there are some functions that are implemented within the FVMesh class to calculate all the necessary geometrical parameters. And then this is basically them calling and passing the init function of the actual FVMesh class. And that's how an object of the FVMesh class is actually returned. Regarding FV matrix, so this is again a little drawer for data, basically, where we are storing the mesh, the field that we are solving for in the case of some matrix, source terms, so A matrix terms, and so on. And this is the main FV matrix constructor, where we then assign data as we need them. And basically this construct function is used, so basically we need to pass the field, the operator as in Laplacian, DDT, and so on, and the scheme that is going to be used for the specific operator, that's for the discretization of the specific operator, and so on. And this function actually define matrix. This is dependent on the operator and scheme and so on. So basically using string evaluation of the operator and scheme, basically the code is pointing to different classes and saying, okay, I need linear orthogonal discretization of the Laplacian term, for example. And that's how source, lower diagonal upper are defined and then passed, and then actually the FE matrix is initialized. This is an example of how it approximately works with a Laplacian term with linear orthogonal discretization. So basically these are just some things that are called and defined. Let's not bother too much with that. But basically this is the loop that actually goes through the internal faces, and then these are coefficients of matrices. If you want to hear more about that, I recommend Professor Jasak's training session later about the finite volume method. But basically this does exactly what you're going to hear from him. So basically goes over all of the internal faces and then assigns matrix coefficients as it has to all of the owners and neighbors. And then after that is done, for all of the internal faces, we loop over all of the boundaries. And then again, using string evaluation, depending on the boundary type, such as fixed value, fixed gradient, and so on, we call what is necessary. So we're in the practical session, we're going to have some examples of these kinds of string evaluations and calling of specific classes and so on. So now to get to one aspect of Python, which is very often an issue, which is speeding it up. So some of the options are, as with most modern codes, parallel computing, of course, just-in-time compilers. We can be smart about how we use some modules. So NumPy is often very, very good in that. It depends on the structure of your algorithms and data and so on, and Cython. So I haven't implemented parallel computing in the case of my code. Regarding just-in-time compilers, they're an option with Python, but I've played around with them a little bit. It didn't get a significant speed up, or I had some issues with compatibility with some packages that I was using. So I basically gave up on, I didn't go for the first two options, but I'm gonna comment a little bit on NumPy and Cython, which proved to be quite useful. So regarding NumPy, for example, it's a Python module that is used for very efficient array operations if, and the if is important, if the operational algorithm that we are trying to do, if they're in an appropriate format. The problem with unstructured finite volume method is that it is unstructured. So that does not work well with NumPy. So below, there is an example of how NumPy is used. So if you do this in regular Python, this is the way you would be smart about it, how to do it in NumPy. So the thing is that Y and X here are equally sized arrays. And in the case of unstructured volume data, we simply have operations that we have to loop over all of the cells, and then depending, we have to point to neighbors, owners, and so on. So basically, this kind of simplicity is in most cases not possible with NumPy for unstructured finite volume method. However, there is a useful thing which is called Cython. So basically, Cython, so Python itself is basically C code, but it's packaged in a way that it's simpler and easier to use. And Cython gives us an option to pre-compile Python code and assign types to variables. So the reason why Python is quite a bit slower by default is because it's doing a lot of type checking and it's not pre-compiled. Cython helps us to go around some of those issues. So it can be only several lines of additional code for a significant speed up. So basically, as you can see, if you want to do the same operation as in last slide, you simply need to first define the types of the variables present in your code. And it's almost as simple as that. Then you have to just like compile it, simple step. And then it becomes C code. So for some benchmarks, this one simple benchmark is let us calculate fractional of 10 and repeat that 10 million times. So with Python, on my machine, on my laptop at a given time, the execution time for a very simple way of doing this was about 5 seconds with Cython. So basically the same thing, just with declared types of variables. I'll give a better example after this. It was orders of magnitude faster, quite a bit. With NumPy, it wasn't as fast because we were only calculating, we're not using NumPy smartly, let's say. So it does offer some speed up, but because it wasn't a big array of a lot of data, NumPy didn't really have a lot of strength in there. And these are C++ codes with different levels of optimization. So we can actually see that after, in between 01 and 02, C++, the compiler was smart enough to realize that we are actually doing the same thing for 10 million times, and it, well, protested, didn't do it 10 million times after 01 optimization. So basically, we see that Cython is of a similar order of magnitude to C code, but still usually somewhat slower than actually properly optimized C or C++ code. This is a similar benchmark, but in this case, we calculate the fractional of all numbers up to 10. So 1, 2, 3, 4, 5 to 10, and then store those values into an array and then repeat that 10 million times. So the white times in the table correlate to the white code as you can see it on the screen. So basically using Python, which is the white code here, so without type declarations, we get 21 seconds of execution time. Using Cython in a naive way, in this example, that means that this was simply compiled. So no type declarations were defined without any of the red or green code. And basically here we see that just the difference that the compilation makes, instead of compiling on the run, as Python by default does, we get about a 10 to 15% speed up. In the third scenario, we defined the types of the individual smaller, let's say, variables, which is integers in this case, so X and repeats I and J. And then we get a twofold improvement in computational time as compared to pure Python. And then in the last case, which was the biggest and most massive improvement, is basically when we defined that this results array is actually of it's a NumPy array that contains integer elements, and it's of dimension 1. So it's 1 times 10, not 5 by 10, not 10 by 10, and so on. So here we got basically, as you can see, a massive improvement in computational efficiency. And so in the case of my code of FOAM Python, so this is I use cprofile, which is a sort of default way of profiling your code in Python. Then I use SnakeWiz to actually visualize the results. So I hope you can see somewhat clearly, but this says simpleFOAM.py, which is basically the whole file. And then underneath that, we have a FV matrix solve function. And 90 to 95% of the solution time was taken up by the solve function, which is, I think, reasonable for a computational continuum mechanics code. So what I realized here is that there are basically two functions which sort of corresponds to two files that were taking up almost all of the computational time. So basically, if you see this is everything else, and these are two files / two functions. So after I Cytonized this using the techniques, type declaration techniques that I presented before, I get this. So basically, if you remember this number 661 seconds, we get 8.6 seconds, which means that specific function and that specific segment of the code was sped up 75 times. And then we have the rest of the code. If we went through all of those files, we could get a similar speed up, but this was basically the low hanging fruit. So that is an example in my code. Yeah, okay, so now we discussed a little bit in general about the code. So if people want to follow, they could. I hope I'm not going to be too fast in the interest of time but yeah, we can get on it. So I'll leave this a little bit on the side. If anyone wants to actually download the repository, it's going to be publicly available and everything. I'll try to see. But even if you don't manage to follow, I think it's fine. I think my points will come across. I'll type it in the chat, hopefully. It's gonna help. So I sent this middle thing in the chat on Hrvoje. So if you need it further, I'll let it be on the side for a bit. Well, I'm not sure how much you can see this way, anyways. So I think I have it already. So let's okay. Okay, so I'll do it in the same way. Okay, so now I have downloaded the code, and basically the things that I'm going to do with the code is, number one, we are going to run some existing tutorials which already exist in the Git repository, so similar as in OpenFOAM, like you can find the tutorials folder. And we are going to implement a new boundary condition. So basically, for the first part, we're going to run some simulations. So to go into the folder, so I'm going to use the three functions. So just to give a little overview. So basically, similar to OpenFOAM, we have the applications and solvers folders. Benchmarks are simply some benchmarks that I've run here and actually presented the fractional results and so on. Scripts are actually scripts which you can copy into the top level folder and then run them to basically use Cython to Cythonize the code, to actually precompile the code in Cython. But it can be used even if you do or don't. If you don't use that, it's going to be a little bit slower, but that's fine for the session. I'm going to actually do it probably at some point to just demonstrate the differences in speed. And in the SRC folder, similar as in OpenFOAM, we have well, stuff, you know, FVC, FV, you see probably a lot of familiar terms, FV mesh, FV solution stuff, field stuff, and tutorials and so on. So from tutorials, I have some, so icofoam, so lid-driven cavity example, Laplacian foam, also cavity example. I have some profiling tutorials, in simple form, I have a 2D pipe. I have, again, the cavity example and Pete's daily. So to start, let's go do a simple thing, which is go into tutorials, and then let's go into Laplacian foam, and then into the cavity tutorial. So I think when you first run it, I think if you never used Python before, I think it should complain about NumPy and psutil, and which should be easily downloadable using pip. So I hope you have experience with that, but basically that shouldn't be an issue in my computer. So I'll simply run it just for the time being. So basically here you see the code executed, and just to show you, so basically the same as in OpenFOAM, we have time folders for results, and then I'll call foam extend 4.1 to have access to power view. And this is our solution. This is a quite simple one. I don't want to stick to this too much, but let's go into simple foam, also something simple and hopefully familiar, which is Pete's daily example. So in this case, let's run it. What happened? It's a bit slow. So now I'm gonna just show you how to use the existing scripts to Cythonize the code, which means basically go into the top level folder, basically the main Git folder. You can copy the, so there's a folder called scripts, and within that there is something called script set Cython, and you can copy it into the top level folder and run it. Simple as that. So basically what's going on here, it's a script that handles everything that's necessary, nothing too complicated, but basically two files are being compiled, and now we have libraries which Python can import and basically use the code from within. So now let's go back to the tutorials folder, simple foam Pete's daily, and now if we run, I hope you remember the previous speed or lack of speed. Not too flashy, but it's not annoying, at least. Yeah, so just until it runs a little bit. So So basically, after this, we're going to keep it reasonably simple. We are going to implement a new boundary condition, which you can actually see on this slide. So basically, as you saw the Laplacian foam example for the cavity geometry, so we had a constant temperature on top. This is something I called the zebra boundary condition, because it has sort of stripes on top. So basically, it's the same thing as any fixed value boundary condition, regarding the contributions that the FE matrix is going to get, but it's just a thing of having different non-uniform values on the wall. In the meanwhile, we can see the code. Sorry, see the results of our simple form run of the pitch daily solver. Yeah, some pressure, velocity, quite standard stuff. You would get something very, very similar in OpenFOAM. And I wrote the way that the solvers are reporting for the residuals and so on. I wrote that to be familiar, basically, if you have used OpenFOAM. So yeah, let's get to the boundary condition part of the session. There are similar tutorials within OpenFOAM how to implement your own custom boundary condition, and I'm going to do something similar. But basically, the way we're going to go about it is we're going to try to use something that doesn't exist, which is something that Professor Jasak likes to refer to as the banana trick. So basically, requesting a banana, and then the code is going to tell you, well, I don't have a banana, but I have Gauss-Seidel, I have this solver or that solver, and so on. So we're going to do the same, but with Zebra. So let's to go back and let's copy Laplacian foam folder into Zebra, for example. And then to go into that, we're going to go into the cavity folder. Let's just try to run it to see if everything works. Yes, it does. Excellent. So let's use this terminal to navigate the code, basically. So within the case folder, we see some scripts used for running or setting up the simulations, and we see the case setup.py file. So let's take a look at that. So this is syntax that you have seen previously when I was describing the code. And in this case, we have a top wall or the moving wall with temperature of 373 Kelvin and fixed walls with 273 and so on. We have the definitions of the internal field, connectivity used in the solver, start time, write time. So again, very similar terms as used in OpenFOAM. DDT scheme, Laplacian scheme, is it runtime modifiable or not? And then the properties, tolerances, and so on of the solver that is actually used in the solution of the code. So how we would go about implementing the Zebra boundary condition. So let's say we want to do it for the top wall. And if we run the code, Python is going to complain, of course, because it doesn't exist. So there is a function. There's a function which said, okay, I'm asking for set boundary values functions dot Zebra, and it basically didn't exist. So the way we can go about that, we can grep is useful. If you don't know, so basically I know my way around the code, but I'm going to try to pretend as if I don't. So let's look for this, or actually, it's actually saying us which file specifically is the problem. So we can go into that. And it says the problem is at line 106. So basically, this is, as I previously mentioned, that I have like drawers for data and so on. This is something like a drawer for functions which define stuff depending on the boundary condition that's used, or in some other example, depending on the linear algebra solver that you're using, and so on. So basically, in this case, it's complaining that it can't find it. So if we look for this within this file, we see that it is used, but it's not defined anywhere, which is because class volume field inherits from volume field boundary conditions. So basically, so you don't have to dig around the code. You can simply grep recursively from the top level folder to find where whatever we need is actually defined. So basically, we are looking for volume field boundary conditions where this class or drawer is defined. So this is, in this case, this folder, which contains the boundary conditions for volume fields. And then basically what we see here is exactly that. So this is the drawer that we're looking for. Here we have fixed value, empty in the case of 2D simulations, fixed gradient, and calculated, and that's about it so far. So what we want to do is zebra, which is quite similar to fixed value. And first thing first, let's try to just do something that does the same thing, but it's named differently. So let's simply try to do this. Zebra equals, so as C++ people might not know, functions in Python are very simple objects, basically. So you can basically juggle with variable names and say, okay, this function is actually this function and so on. So this is exactly what we are doing now. And now, from this point onwards, there's going to be a function within this class. There's going to be a function that is called zebra, but does exactly the same thing as the fixed value function. So now to try to run the code. Another complaint. Why? Because now there's another sort of drawer for data that does not contain the necessary zebra function. So let's again try to grep for that. Okay, that's for the sake. So again, similar thing. We were looking for where that thing is implemented for a volume scalar field, because we are dealing with temperature. In this case, in this solver. So to open this file. Sorry. So in this file, the error is in line 300. Sorry, am I? Seriously, I might be. This is kind of not helping me explain how easy it is. Okay. And there is something called right boundary values function. So copy skills or not. Today. Okay. So basically these functions are used when the results are being written to write boundary conditions. So why this happened here is because the code was trying to write down the initial state in the folder 0, so we can actually visualize it in PowerView as well. So in this case, same as in the previous example, let's try to just get a function that's called same as fixed value. Sorry, called same but does the same thing. Called differently but does the same thing. Let's try to go again. Again, another mistake, but we could do the same thing. So let's grab for linear orthogonal scalar because we see that that's a problem. So we see that it is defined here. Sorry, give me a second. Okay, let's try this. It's going to be here. Yeah, sorry, because the last thing that complained was scalar gamma, and it had no attribute zebra, so we have to open that. So class scalar gamma, and that, and then try to look for scalar gamma. Same trick. So zebra is going to get a bit more interesting after in a bit, I promise. Again, and I think we're going to get the same issue one more time. So now there is an object or a class called set boundary values functions for the gradient, for gradient calculation, and it's also complaining. So let's try to find that. I think it should be one last thing, and it's again in volume field boundary conditions. we're back to the same file that we were in initially, but this time we were looking for the same thing, but for gradients, for calculation of gradients. So we see a fixed value function, and basically here we see that some other function, not only zebra, inherits in a way from fixed value boundary condition. I think this would hopefully be it. Okay, great. So basically we now copied fixed value, the fixed value boundary condition into a boundary condition called zebra. But so far, let's see the result. So far, it should not really do anything as compared to fixed value, because it's the same thing. We simply copied it. So as I said previously, the zebra boundary condition that I'm talking about is the same thing as fixed value in terms of matrix contributions, but it simply has different non-uniform values defined on the top surface. So the way we would go about that is in this set boundary values functions drawer, and basically we would copy the fixed value function and modify that. So basically the same thing that you would do in OpenFOAM. You find something as similar as possible to your use case, and then you modify that slightly, hopefully, to get your desired behavior. So in this case, we're gonna have to copy it and then modify the name. And just to check if it also works. It luckily does. And then basically, let's go back to the case setup thing. So in this case, what we want to give it is we want to say, okay, use something that's called zebra. And then we do not only want to pass the one value, we want to pass two values, basically for both black and white stripes, let's say, but also we want to have a parameter, a variable that defines how many stripes we have. So we're going to put that into a dictionary. And then let's say that the first thing is going to be called, let me cut this. The first thing is going to be called number of stripes. And then to start with, let's say 4. The second thing is going to be the first value that we want to use, which would be, let's say, again, 373 degrees. And then the third thing is the other value that we want to see on the other set of stripes, which could be, let's say, 273 degrees. So to get a similar result as visualized back there. So I think syntax-wise, this is all right. Yeah. So if you try to run it again, well, it complains at some point. Why? Because it simply does not define the thing that it should for fixed value. So we go into this function that we just created, and basically what happens is we can actually even see this. So there's obviously a problem with the specified fixed value, which previously was 373 Kelvin. And then if we want to preserve the same behavior, we can simply do this. So basically, from the thing that we are passing together with the name of the boundary condition, let's say we only want to use value 1 from the dictionary. We're on it now. Sorry, a second. So I'm passing it. I'm not sure why it doesn't work. Give me a second. Okay, now you're getting a bit of debugging demonstration as well. I have tested this extensively. This works. This works. Okay. If anyone sees a syntax error or something, I would be very grateful. Yes. Okay, sorry. Or no. I honestly have no idea. I honestly have no idea.
You're trying to use a value as a key. Is this really the intention here?
So here, so value 1. So this should return. Sorry. I'm trying to retrieve this. But it's that's it's a good question because this transcript. Mm-hmm. Okay, thank you. Nice trick. So we are here. I honestly have no idea if this worked beautifully previously. Wait a minute, sorry. Sorry, this is, wait, no, sorry, no, this is a new mistake. I don't. But this is what I do want to get. That's what's bothering me. I think that's right. I think that's right. What if I do this? I'm very sorry, guys. This is exactly. I don't get it. Sorry, I really don't get it. I would prefer to do questions, but the point was to have a demonstration of how easy it is to do it. I hope you appreciate that. But it should be easier. But yeah, if you if you forget some syntax in the last moment, that doesn't help. But basically the point was to get this solution and then basically to using this file, runtime select if you want 4 stripes, 5 stripes, 6 stripes, and so on, and to get this reasonably simply. Yeah, I can post that code later in the Git repository. So just to see how it should have been done. Basically, I'm going to update the Git repository, and if anyone is interested, you can see how it would be correctly implemented. But yeah, I can see if there are some questions. If anyone do you have anything opened, or should Fran? Okay, yeah, sure. Actually, if there's any questions in general. So thank you. Thank you.
It's very interesting.
Thanks.
Very useful for understanding the potential of Python and so on. You think it's just this kind of Python development will be useful for education, as you brought at the beginning? How do you see the different aspects when you have them to keep it updated, keep it more close with your feature version, including new features? And if you can comment a bit on that. I think it's really interesting.
Yeah, thank you. I think for educational purposes, it's good. Honestly, I think it's much simpler to basically get to the bottom of how the code works than with OpenFOAM, because I was also, but by this point I am an OpenFOAM programmer, but at some point I wasn't. So basically I know that those beginnings can be a little bit more difficult with C++ and OpenFOAM and so on, because it's well written, but it's simply big and complex. So yeah, educationally I think it's good. Regarding the actual usability, I think that's a broader discussion. And then I'm not an expert by any means, but if you take, as far as I understand, the machine learning, for example, as a field, the way I understand it is that basically most of the modern currently used solutions are basically C code wrapped in Python. But I guess it's a discussion of, is it worth it? Because I think in their case, they have a lot of similarly structured solutions, systems of equations and so on. So I guess it's worth it to basically write one sort of C functionality and then couple it with Python, because you're going to be doing the same thing a lot of times. With CFD, I think it's a bit more varied, because I think it's a bit more difficult to pack it up like that, wrap it up like that, because there are going to be so many applications that have to do so many things at so many different levels, from the ground up, from the ground being, storage of FP matrices or whatever, to up to being like actual solvers and actual physical applications. So I think it's a matter of, is it worth it? I don't have the answer to that, but I think it's possible in the future that this is going to be sort of the simple low-hanging fruit solution, basically having Python and then in some way wrapping C code in it, because Python itself is simply not fast enough for industrial cases, no way. Not even academic. But if you use tricks like this, maybe for academic purposes, where you write the code that solves some niche issue once, 5 times, 10 times, but if you are trying to sell a code to an automotive industrial manufacturer or whatever, yeah, they're probably going to be happy with it. But maybe in the future, maybe depending on how the field develops. Thanks for that question.
Yeah, thank you for your talk. Let's see. Yeah. I just have a question about the usage of what you presented. I think OpenFOAM for a beginner has its own difficulty in terms of someone thinks that, oh, I need to learn C or C++ and then OpenFOAM. Just my question is that someone wants to just get into this new pool. Isn't a new question mark there? I need to learn C, then C++, then OpenFOAM, then this
Mhm.
one. Isn't like that? Or how independent do you think it will become for it? How standalone do you think it will become in future to just be a
Fair
like,
point. So from my perspective, I think just knowing Python is a skill that, you know, modern developers should have, like whatever kind of, I mean, not necessarily obviously, but I think it's useful to know. Never mind this code. So if you do know it, I think it's reasonably simple and easy. I mean, I know what you're talking about, and learning OpenFOAM to use it to run cases is one thing, and people think it's very difficult, and then they learn it, and then they start to code, and then that's another beast, another animal. And if you're trying to understand the fundamentals of finite volume method, of how matrices are constructed, of how the arrow matrix format works, and how linear algebra solvers access stuff that they need from the FP matrix, I think it could be useful, because I think basically because there is less code, there is less stuff pointing you around all over the code, and it's not over 1 million lines of code, it's over 2,500 lines of code. So maybe it's worth a try, especially if you know Python. If someone is just learning how finite volume method works.
you think that it will be possible that if, for example, if I don't know anything about OpenFOAM, I just start from scratch and start from the start point with this one?
Could be. If you follow, for example, I mean, that's what I did, to be honest. So I followed Professor Jasak's lectures to find out how finite volume method works. But then eventually when you implement something, that's when you actually understand it, right? So this could, I mean, you could do the same in C++ and OpenFOAM, but I think it's more code. It's more complex code. So I think this is sort of a compromise where you don't have to like actually implement something to understand it, but maybe it's more reachable to actually see how it's implemented, as opposed to OpenFOAM when you start digging. Like depends on how much your supervisor is pressuring you to actually do something. You will or won't do it. Whereas here you might not give up as easily because it's possibly simpler to reach, easier to reach a goal.
Yeah. Thank you.
Thanks.
I have one comment and also a question. First of all, I think it's a very interesting work, and I believe it could be also good if you want to prototype a new solver to at first do it in FOAMPy.
Yep.
Because if you do in C++, we implement something, we compile it, it does not work.
Yeah. I personally use Python like that for a lot of stuff, not only for solvers, but like if I have some algorithm that I never implemented before. Exactly. Yeah.
And the second question which I have, does FOAMPy also run in parallel? So, or did you?
This thing, no. I haven't implemented anything parallel computing wise.
So no MPI and.
No. I'm sure it's
system.
possible, but I simply haven't delved into that. No one has offered me enough money to do it. So.
Any more questions?
Yes, please.
Okay, so let me see in the chat. So basically, the first question was relating. I'm pressing. So can you hear me?
Yes.
Yeah. Okay, so the first question was, I don't quite, by Patrick Hahn. Basically, he was asking when you were doing the debugging, if couldn't one also use a Python debugger instead of graphing? This way, one can take advantage of the interpretation in Python.
Sure, whatever is convenient for you. I totally, completely agree.
Okay, there is also another question. Let me see. It's from Axel Dorian. He is asking if we can simply consider FOAM Python as calling Python modules in OpenFOAM.
Sorry, as what?
Can we simply consider FOAM Python as calling Python modules in OpenFOAM?
I wouldn't say so. It's I'm not sure I fully understand the question, but it's completely rewritten. Like everything is written in Python. So I'm not sure what's exactly the
yes, if Axel wants to reformulate the question,
but
I'll read it again.
of course, whoever is interested in any more questions, feel free to reach out to me through the platform and so on.
Okay, there is another one. Gerasimos, we were able to just ask it directly. So Gerasimos is asking, so is foam Python the phoenix of Dolphin?
Of course.
Okay, do you know the projects? talking about?
No, not really.
So
The Phoenix
this
sounds
has
cool.
some other finite element framework that under the hood has a C++ implementation, but I think the way it actually got popular was through a Python wrapper, which is called Phoenix.
Yeah.
And I'm now wondering if this is really taking OpenFOAM to a new level that could allow people to just write Python code but still execute OpenFOAM. So I was not sure. Is this actually calling OpenFOAM under the
No.
Yes.
This everything is written from scratch in Python.
Okay, so completely different project then. Okay.
Yeah, but I mean that's related to this, like some comments that I made previously. Like maybe that's the best solution, but realistically, OpenFOAM was written when Python was not really something that people just picked up at the time, and there's a lot of inertia. You have a lot of code, which good code, so it's not as simple as just oh, let's just write it in Python. So there may be some work to be done there. I agree. That's an interesting idea.
But what is the original motivation then for not reusing OpenFOAM under the hood?
I want to write it in Python. I had enough time to do it, so that's about it. But a good point. Good point. That's something that would be interested to look into. I agree.
Thank you.
Hi. So it was a very good talk.
Thank you.
The question I posted is, I don't know, like, is it like a utility in OpenFOAM, the Python that you have mentioned?
Okay. Oh, it's a general thing. It's not related to OpenFOAM. It's you can download it using pip. So as all other Python modules like NumPy, SciPy, so it's included in Python in a way. You have to download it through pip. So it's a Python thing.
Okay, and can I use this for Solid for Foam or Foam Extend 4.0?
I wouldn't expect so, because this is basically compiling Python code, existing Python code. So I mean, if you basically you can use it to speed up any Python code.
Okay, thank you.
But if it's C++ or yeah. Thanks.
Thanks.
There's a question. I think you should, because the online audience.
So my understanding of what you've presented is almost like an emulation of what OpenFOAM
Yeah.
is, just in Python.
Yeah.
Is that correct? With regards to the motivation, what's your end goal?
There is no end goal. I literally had enough time to do it, and I just did it. But the end goal is it's public if people want to use it for educational purposes. If there is some traction to get something more interested going, fair.
With that in mind, have you thought of it instead of using it as an emulator for Python, but actually developing it as a teaching tool? Because learning from someone learning OpenFOAM, not only do you have to learn OpenFOAM and C++ and how everything works, but you've also got to learn into Linux. Whereas with Python, that's available through Windows and very much a coding baseline now. So maybe that's a direction that you can take it into.
Yeah.
I mean, what do you think about that?
Fair point. I mean, basically, your point is that it is more accessible just because it's Python and
Exactly, yeah.
not on Linux and whatever.
Precisely.
Sure. I mean, good point. It's online. It's a matter of advertising it correctly, I guess. So I guess that could be a way I could take it for it to get some traction and popularity.
Yeah, it's more of just to give it a direction instead of going through tutorial by tutorial. And
Yeah. Fair point.
obviously for testing purposes, it's perfect, but yeah. Great. Thank you.
Cheers. Thanks. Okay, thanks. Doesn't seem like there's any more questions from the live audience. Marko, is there any questions from? Okay, I guess we are done then. I'm not sure if we have any stuff to help us with that. Okay, thank you. Thank you all for coming. Thank you.